I forgot to actually put out this warning for every other section, so you guys will know a little bit more. You are working with concentrated nitric and sulfuric acids. They are extremely corrosive. They will burn you. This lab, more than any other lab, usually at least one student gets a relatively quote-unquote severe burn, which just means they got a spot of acid on them and it burned them. Okay? So it's not like it's going to be life-threatening, but it is something that you need to be aware of and be careful working with the acids because they are dangerous and they will cause burns. Okay? So please be aware of that when you're working with them. Also, this material you've apparently already seen in lecture and been tested on. So in theory, this can go kind of fast. So we'll start off kind of slow, and then I'll ask more and more questions as we go. A good symbol for our electrophile, because we're looking at electrophilic, would be E for electrophile. Most electrophiles will have what charge? Positive charge, because they're electron loving. They want electrons. They'll need to be positive if they're going to be attracted to electrons. Aromatic, a good symbolism for that would just be a benzene ring, which as far as you guys are concerned, I'm pretty sure that's all you really have to worry about. We hear the term aromatic. And then substitution. So we're doing some kind of substitution reaction. We'll be looking at a reaction arrow. So if we're going to do a substitution reaction, we're going to have to trade two atoms. What two atoms do we trade? As a hint, I'll give you the easy one. The electrophile is going to have to trade for something. Okay, why hydrogen? What's the other option?
Those are the only molecules bonded to carbon.
So it's carbon and hydrogen are your only two other options. Why would we do the substitution with hydrogen and not carbon? If we tried to pull a carbon out, how many bonds would we have to break? Keep counting. Keep counting. 4 bonds. We'd have to break each of the 4 bonds that hold the carbon atom inside the aromatic ring. Okay? So that's a lot of bonds to have to break to try and do a substitution for the carbon. Okay? Taking a step further, which is more accessible for the electrophile to try and do a substitution reaction with? The hydrogen. Why the hydrogen? It's outside the structure. Almost all hydrogens are more accessible than carbon atoms because they're held on the outside of your compound. Okay? So that's what we're looking at. We're trying to do this overall reaction. So now what we're going to do is evaluate how it occurs. So we'll look at a mechanism. So we'll start with these two reactants. Of these two, which one's the most reactive? Which one would you look at and say that one's unstable? E. Why E? Okay, it's got a positive charge. How can we stabilize E? We need to give it a negative. So we could look for a negative within benzene. Do we see a negative? No. So instead of looking for a negative, we need to look for something a little bit more mild than that. We need to look for electrons. Where are there electrons within benzene? Pi bonds and sigma bonds. Which bond is going to be most, or which set of electrons will be the most accessible or reactive? Why would the pi bonds be more reactive? Higher in energy than the hybrid orbitals of your sigma bonds. You're looking at S-type orbitals. Okay? Your pi bonds are held further away from the nuclei. They're more reactive. So we can take a pi bond and react with our electrophile. What ends up happening? Well, we get our first product. That looks kind of small. Let's try that again. It's a little bit better. We did not react or move the hydrogen, so that's still there. We've got a positive charge up there, and we didn't touch the double bonds. Okay, is this structure stable?
No.
Why not? It has that carbocation, that positive charge. What do we need to stabilize the positive charge? Okay, do we have a negative charge? Nope. So what do we need to do? We need to look for electrons or find an electron source. Where are there electrons within this structure?
In the other bonds.
Which bonds?
The pi bonds.
We've got pi bonds and sigma bonds. Where do we want to get electrons from? The pi bonds. Why the pi bond? They're easier to break. So we'll go ahead and move a pi bond over and see what happens. When we do that, we didn't change our electrophile or our hydrogen. We didn't change the other double bond. We get a positive charge up here. What's the relationship between these two structures? They are resonance structures of each other. We can specify that by making sure we got the double-headed arrow. That sounds like fun. Okay. Is this structure stable? Nope. Still got the positive charge. How do we stabilize it? Okay, so we can try and move the other double bond. Okay, what do we get in that case? Be another resonance structure. Not quite the same thing, just over again, but pretty close. Is this structure stable? Why not? Still has a positive charge. So what do we do? Could be not a bad first approximation. We should then pick up the pencils and try again. Moving the pi bonds didn't help us. Okay, that gave us some resonance stabilized intermediates, but that doesn't finalize and get rid of that positive charge. Okay, so to formally remove the positive charge, I'm going to have to bring in or get electrons from somewhere else. Okay, so what we're going to end up doing is taking the electrons away from the hydrogen. So now we're going to attack the sigma bond. So we will take those electrons and shift them into the ring. What's the result? I now get a benzene structure with my electrophile on there and H+. Okay? So I end up swapping where the positive charge sits, either on the electrophile or on the hydrogen. Hydrogen being the lowest electronegativity, it's probably not that bad off as a positive charge. Okay? So now we've pushed our overall reaction. Okay? Why did we not show that from the get-go, that last mechanistic step with the sigma bond? Why did I draw these two structures? Why bother? Couldn't I just done that from the beginning? Done the removal of my hydrogen?
No, because the positive charge is on the carbon.
So I could have still just moved just as easily, so I'll go through and show it with a blue arrow this time. I could move the electron here, here, here. Why show the resonance structures? Ultimately, what we're trying to do is show all energy states. Cover our lowest energy options first, and if it happens to mean drawing a new structure, we have to draw that new structure. Okay? In this case, we end up drawing those three resonance contributors. Okay? The reason these three are going to become more important is when we go through and change our benzene structure. Because then the hydrogens on that ring are different from each other, and we would expect different products. Okay? So these three structures have a lot of importance as far as being able to predict chemistry. Okay? Because they're so important, we give them a special name. So we're looking at our resonance contributors here. That's not the special name. We got a better name for it. What's the difference between these three resonance structures and, say, the starting material and the product? Okay, they're intermediates, but I want you to go closer to the structure. What's different about the structures? There's a big hint. Let's take a look at this blue carbon. What's special about that blue carbon, say, from any of the carbons in our starting material or product?
It's the only one that has 4 bonds.
Close. They all have 4 bonds. This one has 4 sigma bonds. Okay, no pi bonds. What hybridization would this atom have? SP3. We already addressed the primary concern with it. It's got 4 sigma bonds, no pi characteristics to it. These structures
So the rest of them have SP2.
they're all SP2 hybridized. These structures get referred to as sigma structures. Sigma structures, or you might even see sigma complexes. Okay? These three this type of resonance here is going to become critical to answering the post-lab questions. So you need to be aware of how to manipulate these. Okay? So now that we understand how the reaction works, okay, or almost understand, what are we reacting here? What did E stand for? We had an electrophile. What does that mean the benzene ring acts as? It is aromatic. But if we're going to look at reaction classifications, what do electrophiles react with? Nucleophiles. So we've got a nucleophile. Now that we know how the reaction works, we know what our pieces are, let's make this reaction go faster. How can I make the reaction go faster? Okay, right idea, but let's get at what the catalyst would do. Okay? Our electrophile was what charge?
Positive.
What's the charge on my nucleophile? What's the charge on the nucleophile right now?
No
It's
charge.
neutral. What if I made it negative? Would I expect it to react faster?
Yes.
Why?
Because the charges are actually attracted to each other.
Charge. We're starting to neutralize those charges. So if I can make the nucleophile more negative, it should react faster. What happens if I make the electrophile more positive?
The reaction rate would go down.
Okay, what charge should the electrophile be? Positive. What happens if I make it more positive? It should increase the rate because it's now more reactive. It's more charged. It's more likely to, or more wanting to neutralize that charge. So what we're looking at in almost all reactions is changing the speed of our reaction by making our nucleophiles more nucleophilic or our electrophiles more electrophilic. How we go about doing that is tricky in some cases. We're going to go ahead and look at the electrophile first. Since it's not something we're doing in lab, I don't expect you to know too much about this, but you should be able to go through and answer this question. Which of these electrophiles is the most electrophilic? Middle. Why the middle one? It has the positive charge. Between the next two, which one's more electrophilic, right or left?
Right.
So let's circle an atom. That atom and this atom are the most electrophilic of those two groups. Which one's more electrophilic, the carbon or the bromine?
No, I was thinking carbon.
Why the carbon?
Because it has
They
SP13
both have 8 electrons around them. I don't even want to get into hybridization. It's easier than that. Yeah. What's the carbon connected to? Chlorine and oxygen. What can you tell me about chlorine and oxygen? They're both electronegative. They're going to withdraw the electrons away from that carbon, making that carbon partially positive. Bromine is electronegative. I completely agree with that. But when I attach an electronegative bromine to an electronegative bromine, what kind of bond do I have?
covalent.
It's a covalent bond. There's no partial charges associated with it. So we would predict our rightmost to be the next most electrophilic, and the next one third. Okay? If I want to make these react faster, we won't look at the middle one because that one's already positive. Let's look at the outer two. If I want to make them become more electrophilic, I need to establish a stronger positive charge on each of these. Okay, so there's 2 common catalysts we can add. One of them is iron tribromide. What can you tell me about the iron in iron tribromide? What's the difference in electronegativity between iron and bromine? Big or small? Big. How do you know that?
Because there's an
It's a metal and a non-metal. We've got ionic bonds. So that iron is going to be exceptionally positive. What does an exceptionally positive iron want to stabilize itself? Negative. Do I have a source of electrons nearby? Yeah, I've got the bromine. So I could do a coordination bond between one of those bromines and the iron. How many bonds would that bromine then have? 2. How many bonds should bromine have? 1. As far as we're concerned with organic chemistry, our halogens only have 1. Okay, so if it now has 2, we're going to have to break a bond, and it needs to take those electrons with it. Okay? The only bond we could break, or we've got two options. One, the one we just formed. That's a bit boring. So let's take the other option. And we'll move those electrons towards the bromine as well. What happens to the circled bromine? Loses electrons, ultimately becoming positive. What did we just do? We made a neutral bromine positive. We made our electrophile more electrophilic. Okay? The other common catalyst is we can add aluminum trichloride. Aluminum's a little bit extra special because the hybridization on that aluminum is sp2, which means it has an empty p orbital. What can we put in an empty orbital? Electrons. Do we have electrons? Say on that chloride. What's the special, or what's the issue with chloride sharing its electrons? How many bonds can it have?
One.
One. How many does it have right now? Two. So what is it going to do? It'll take the electrons between that carbon-chlorine bond, pull those towards it. Okay, this one I just kind of want to draw out because it's kind of fun. I personally find it a little bit silly. Remember that. Okay, it'll become relevant here in a second. We get this carbocation, and we could draw out AlCl4. Cl4. Sorry, I forgot what I was writing. Got too excited about the next part. Okay, positive carbon. Can we stabilize that? Do we have electrons nearby? Say on that oxygen. So that oxygen can share its electrons with the carbon. We form the triple bond between the carbon and the oxygen. The oxygen becomes positive. Where's our electrophile in this molecule, the carbon or the oxygen?
The oxygen.
Tricky question. For oxygen to act as an electrophile, it must accept electrons from an outside source. Can oxygen fit more electrons around it? No, it's already reached its octet. Okay, so it cannot accept more electrons. So even though the formal positive is sitting on that atom, that's not where our reactivity lies. Okay? Which atom is our electrophile? It's still the carbon. Carbon is less electronegative than oxygen. Those electrons spend most of their time on the oxygen, putting our reactivity on the carbon. Okay, why did I like this one? This compound has a special name. You guys remember what I said you shouldn't forget? Because it was going to become relevant here in a second. What's the name of this? It's kind of a fun name. Some might refer to it as kind of a silly name. Some might even refer to it as an acylium. Da-da-da. Yeah, there we go. It's an acylium ion. Kind of interesting, just kind of fun. Okay, our reactivity is at that electrophilic carbon. Okay, so at least half of you laughed. At least that's what I'm going to decide. Make me feel better. So we're going to add our catalyst to make our electrophile more reactive. When we shift to the aromatic ring, okay, with the aromatic ring, what did we say it acted as in our mechanism? Don't get all overwhelmingly loud. I can't interpret too many words. We're looking at our aromatic ring acting as a nucleophile, which means it has to donate electrons. So when we looked at our benzene ring, didn't have a whole lot of reactive electrons, no negative charges. We just had the pi bond. Okay? So what we're going to do is say, I want to change that structure. If I try and put in a catalyst, we want to drive electrons into that compound, or into benzene. Which atom can hold more electrons in benzene? How many electrons are on each of those carbons right now? 8. How many electrons are supposed to be around carbon?
6. No, never.
Greater than 7, less than 9. 8 electrons. Octet rules. Okay. Can I put more electrons around an individual carbon? No, it cannot satisfy it. So I cannot add a secondary reagent or catalyst to put more electrons in. So what I'm going to have to do is change the structure of that benzene and hope that we can increase its reactivity. So what I'm going to do is substitute hydrogen for atom X. Okay, and there's a couple different descriptions that we can go with that atom X. So let's go up first. What can you tell me about atom X in that top position? Okay, but hydrogen didn't have any charge either, so that's not a big difference. Give me another one.
It has 2 electrons.
It has more electrons than a hydrogen. Our characteristic there would be a lone pair. It's not always a lone pair, but that's the one that stands out a little bit more. Okay? So lone pairs are possibilities. What can we do with that? Well, we're concerned about how atom X affects the electron density in the ring. So what I'm going to do is draw resonance. I'm going to take the electrons on atom X and move them towards the ring. When I do that, how many bonds does that carbon then have? Our blue dot carbon. How many did it start with? 4. I add 2 more electrons into a bond. What do I have? 5 bonds. Can carbon have 5 bonds? What do? We'll break a bond. We'll break that pi bond and now put it on the next carbon atom. The resonance structure that we get, I'm not going to draw all the hydrogens, would be this. What is special about this structure? What charge is my ring? Charges the ring. Negative. What have I done to the reactivity of the benzene ring? I've increased it. It's become more nucleophilic. So if atom X has more electrons than hydrogen, it can push electron density into the ring, making it more nucleophilic, more reactive. Okay? I'm going to leave you to go through and attempt the other resonance structures, and you should find that you can put negative charge at those other 2 positions as well. Okay, so I'll mark those with partial symbols. Okay? If we, oh, you stinker. Let's go back and forwards and back. Let's try that again. Okay, careless typing is what it gets. So we got our benzene ring. We'll go through kind of quick here with this sloppy. There we go, close enough. We put negative charge on the ring, which means our reaction went faster, or we activated our double bond or our aromatic ring to react. So we now have an activator. What positions would I expect my substitution to occur at? Well, it's going to be wherever I have negative charge. Where do I have negative charge on this aromatic ring? Which carbons? In theory, you guys should know this from lecture. What's the difference between each of those positions? Is that still not helping? We're looking at our para and ortho positions. Why do I write para first?
Because it's the most stable.
Para is more reactive. It's not stability. Why is para more reactive? There's a steric effect. Okay, the ortho positions are blocked due to that atom X. Okay? What happens if instead of atom X having more electrons than hydrogen, it now has less? How do we get less electrons? How many electrons does hydrogen have? 1. How do we get less electrons than that? Our atom must become positively charged. Okay, it can be formal or it can be partial. How does that affect the electron density in the ring? Okay, well, if X is positive, what do I need? I need to give it electrons so we can shift the electrons from our pi bond out. What does that give us for resonance? If we continue the resonance, you should see that we can put a positive charge at our para and ortho positions. What charge did my ring need to be to react? It needed to be negative. If it's now positive, what happens to the speed of the reaction? slows down. So instead of calling it an activator, inhibitor, good name, but no. Deactivator. Okay? So atom X acts as a deactivator, our ring is deactivated. What position reacts if I force this to react? We get the meta position. The meta is the one that reacts because it's the only one with any electron density. The para and ortho already have positive charges. They cannot possibly react. This covers 90% of the reactivity that you will see with EAS chemistry. The one part that it does not cover would be halogens, which is why we're doing the experiment that we are. If X equals a halogen, what can you tell me about atom X then? Does it have more electrons or less electrons than hydrogen? More electrons. So what would we predict for halogens being attacked or attached? We would expect that they would activate our ring and be para-ortho directors. Interestingly enough, they aren't activators. When you add a halogen to a ring, it actually slows the rate of the reaction. Why would it slow the rate of the reaction? It's starting to look more like a deactivator. So what does the halogen have to do? It has to pull electron density out of the ring. Why would a halogen take electron density away from a carbon atom? Easier.
Because,
Our halogens are more electronegative than carbon. They pull electron density out. So I'm going to tell you now that halogens will act as deactivators, which would then suggest that our substituent or our substitution occurs at which position? Meta position. Okay, so now we've got an interesting dilemma. Two observations. Halogens have more electrons, so we would expect activators para-ortho, but they're more electronegative, so we would expect them to act as deactivators and meta-directing. Okay, so we've got a bit of a problem here on trying to decide where our substituent should occur. Okay, that's what this experiment's designed to do. You're going to go through and test this. You're going to start with bromobenzene, mix your nitric acid and sulfuric acid with it, and you're going to add a nitro group somewhere on that ring. So that's what the line means through the middle of the bond, that nitro is added somewhere on that structure. Nitro acts as a deactivator, which is a good thing, so that when it gets substituted to the ring, that structure is now no longer reactive, which means we only get one nitro substitution. Okay? If we did a reaction where it was an activator, our ring becomes more reactive, and we could see multiple substitutions. Okay? So we were kind of nice in the design of the experiment and trying to make sure that we limit the possible products coming out of this. So we would expect 3 possible products. You get to identify what product you make and then explain why and how that works. Okay? The other big reason why I like to do this experiment is trying to figure out nitric acid and sulfuric acid in this reaction. Nitric acid is what kind of a species? Acid or a base? Acid, I know, it seems like a silly question. We'll cover that in a second. Sulfuric acid acts as acid. Let's go through and run the reaction. If we take sulfuric acid, or we take an acid and we add it to an acid, typically what do we say occurs? Nothing. If that was the case, we never form our electrophile, which is the nitronium ion. Interesting. So when we take these 2 acids, we don't get nothing. Something actually occurs. What did nitric acid do during this reaction? It acted as a base. It accepted a hydrogen ion. So nitric acid, by definition, a strong acid acts as a Bronsted-Lowry base. Kind of neat. Okay? Why does it act as a base? Nope.
Because sulfuric acid is a stronger acid.
Sulfuric acid is a stronger acid. You can take pretty much any acid and force it to act as something else. as long as you make it react with something that's even stronger. Okay? So it's just kind of neat for that reason. Okay, overall experimental breakdown, pass out the activities. You'll obtain the chemicals, mix them together. Be careful with the acids. I cannot stress that enough. You need to be super, super careful. We don't want to deal with any burns. Okay? If you do spill it on yourself, you will be spending 15 minutes in the sink. Okay? And we will time that. Okay? And 15 minutes is a pretty long time, just so you know. Okay? Then you can make them sit in the sink with you. When you set up the reaction, get it heated, a good sign that the reaction is working is that you'll see a brown gas evolved. That's what that brown sludge thing is supposed to be. That's a good sign that this reaction is working. That gas is due to nitrogen and oxygen radicals reacting with each other in the formation of the nitronium ion. Those gases are toxic, also known as smog. Please don't breathe that in. Set that to the back of your hood, let it do its thing, and hopefully get sucked up by the ventilation system so you don't have to worry about it. Okay? Once you're done with the reaction, you'll quickly add it to water once it's cool to the touch. You'll collect your accrued product. You then have to recrystallize. So if you don't remember recrystallization, this is a pretty important procedure. You'll need to go back and review your technique. You'll obtain the weight and melting point. With the melting point, you'll be able to identify which compound you actually obtained, and you can then complete the rest of the post-lab assignment. Okay? The group activity that Shay just